Hello everyone. Today we're going to be talking about manipulation planning, and in particular chapters 12.3.2 through 7 of robotic systems. We're going to be talking about the basics of manipulation planning, in particular the types of manipulations that need to be done for bin picking as well as placing. So this type of general pick and place manipulation is usually divided into 4 different phases. The first one is transit, in which the robot moves from some configuration not grasping the robot to the configuration where it grasps the robot. The grasping phase acquires the object into the robot's gripper. Then the robot transfers the object from one place to another, and then it ungrasps to let the object go. So let's look first at the pick stage of the pick and place process. The first step is to plan the grasp. There's a number of good reasons for this, and the main one is that contact is essentially the bottleneck for the whole pick and place process. So we want to solve it first. And we've seen how to do grasp planning in previous lectures. The next thing that we'll want to do is figure out the approach motion to try to actually acquire the grasp. So this involves moving forward and closing the fingers upon the object from some configuration in which the fingers are a little bit wider open. So this is essentially acquiring the object at the last inch. In this process, we're going to also define what's known as a pre-grasp pose, which is the start of the approach. This will be used later for planning. We'll need to then reach that pre-grasp pose with some configuration of the robot. And so this will be using inverse kinematics and collision detection to try to achieve this pre-grasp pose. And then finally, we'll run some motion planning to accomplish the transit motion. This will be planned to the arm pose at the pre-grasp pose. And so we can either use sampling-based motion planning, or we can also just execute Cartesian paths if we know that those Cartesian paths are going to be feasible. So if you want to look at this in terms of a configuration space approach, the idea is that we have some sort of configuration space with obstacles. One of the obstacles is the object itself, and the robot can't collide with it except to make contact. And so the grasping pose is actually very deep inside of a narrow passage. The pre-grasp pose is a little bit farther outside of that narrow passage, and then the transit motion goes from the start to the pre-grasp pose. So why do we do this approach? There's a number of good reasons. So one of them is that actually we oftentimes will actually use some sort of mechanical compliance or a active compliance controller that will use feedback in order to acquire the object in the last inch. Compliance is the ability for the gripper to conform to the shape of the object and it adjusts its pose in external to the contact forces that it's feeling. There's 2 different ways of doing this. One is passive compliance through mechanical devices, and you can also have active compliance, which uses sensors like tactile sensors and joint position sensors to be able to adjust to the shape of the object. So oftentimes we switch from path tracking to some sort of compliant controller in order to perform the approach motion. So the other good reason for this is that the grasping pose itself is in a very deep, narrow passage of the configuration space of the robot. And especially when so this is a picture of a 2-dimensional translating gripper with some sort of object that looks like a cup from the top down, or a mug from the top down. With the gripper open, you get the C-space obstacle that looks like the shape in the middle. And if the gripper is actually closed onto the edge of the handle of that cup, then you have essentially a 0-width narrow passage to traverse. And so when this object is precisely grasped, the configuration has actually 0 clearance to the C obstacle. And this is going to be really difficult for motion planning. And even due to uncertainty, we may actually deem this as being in collision. And so our motion planners are just going to throw up their hands and say they can't solve this. So the approach component, especially when we reverse it to get the pre-grasp pose, means that we can try to plan towards this starred configuration rather than this very, very deep configuration shown in that left and the right figure. So how do we plan the approach motion? Well, it's fairly easy to define some Cartesian movement that moves from a far off configuration towards the grasp and then closes the fingers. Now, inverting that will then give you what's known as the pre-grasp pose. So essentially, starting from the grasping configuration, you open your fingers and pull back a bit. Next, let's figure out how to do the reach component of the picking process. So given the pre-grasp pose, This will specify the transform of the gripper as well as the finger configuration. Next, what we'll want to do is solve for the arm configuration such that the end effector reaches that transform. After solving for IK, if it's successful, we'll check for collision, and if you're colliding, we'll return failure. Or you could potentially also sample more initial configurations for inverse kinematics and check those for collision in case you might be able to find one that's collision-free. Once you do find a collision-free configuration, then you'll just set the robot's configuration to the concatenation of the arm configuration and the finger configuration, and you're done. Next, you'll want to do transit planning, which you could do through sampling-based planning techniques, as we discussed last time. But sometimes you can also just use predefined Cartesian motions, such as moving in a straight line in Cartesian space. Now, this is safe only if you know that the workspace that you're working in is completely contained within the robot's reachable workspace. Now, we need to sometimes verify whether or not these paths actually are feasible. And so we actually may need to check collisions and reachability rather than just relying on a robot's motor controller to perform these Cartesian motions. So the general idea is that we're going to take small steps along the Cartesian path using inverse kinematics, and then we ensure that we don't have large jumps in the configuration space of the robot so that the movement is actually continuous and doesn't deviate too far from the Cartesian path. And then we'll perform collision detection on each of those configurations along the path. So now let's look at the placing part of pick and place. The first step is to find a position for the object to be placed in and released. So here we'll want to verify that the object will be stable if we care about keeping it stable. If we're just dropping it in a bin, then it doesn't really matter, we just put it somewhere and let it go. In this case, we'll have to verify the reachability of the pose that we've chosen, which involves solving an IK problem, performing collisions detection, etc. Now, we're going back to the point after we've grasped the object. One thing that we're going to want to do is actually slightly lift the object just a bit so that it doesn't remain in contact with the environment. There's a lot of good reasons for this as well. So for example, we want to maybe make sure that the object is securely grasped before we try to then move it. But in any case, this determines what's known as a post-grasp pose of the object. We'll then want to look at where we wanted to place the object. There's going to be a lowering stage where we do the reverse of the lifting. So basically we determine what's known as a pre-placement pose. We're then going to transfer from the lifting pose to the lowering pose using what's known as a transfer motion. Here we're going to have to plan, assuming that the object is attached to the gripper. Now, we may need to, for example, do stability checking to make sure that our object is not, let's say if we're holding a glass of water, we don't tip it over. And we're also going to want to make sure that we do collision detection with the object, between the object and any other environmental obstacles, or also the object that's grasped and the robot itself. So with these, we add new constraints to the C obstacles of our configuration space. Finally, once we've put the object in the placing configuration, we'll then want to let go and retract. So basically the reverse of an approach motion. So if you want to think about what this looks like in C space, we start from a grasping configuration, and note that these obstacles look different. If you want to rewind a little bit and take a look at those other C obstacles, you'll notice that these are different. That's because we no longer have to worry about making collisions with the object and our gripper, but the object is held and we don't want to run the object into obstacles in the environment. So the C obstacles that are corresponding to these other environmental obstacles have a different shape, a larger shape than before. Now what we'll want to do is then pull back from the grasp configuration to a post-grasp configuration, execute a transfer motion, get to the pre-placement pose, and then move to the placement pose. Finally, we'll then want to do the retraction. So why do we do this, lifting and lowering? So, although it's pretty clear that grasping involves narrow passages, it's not so clear that transferring also involves narrow passages. So there are certain transfer tasks where it's pretty clear that there are some narrow passages. If we're trying to insert a peg in a hole, for example, two objects that need to be assembled together, or the cap of a pen and the pen itself, it's pretty clear that there's not very much clearance between these objects. Now, if you don't have a peg and hole type problem, there's still an unusual C-space geometry here. So you can see that in the y direction for this two-dimensional problem, there is an obstacle, but it's only a half plane, so it's not really that interesting. There's no obstacle in the x direction. But if we start to think about what happens in the orientation direction, there's actually going to be a cusp in the free space. So if I were to rotate just a little bit in any directions, I'm going to cause an increasing collision. So the C-space actually looks something like this. So in the theta dimension, the feasible set is over to the bottom right of this figure, and the infeasible component is to the upper left. And so in order to go from one point to another, we have to make a movement out in the feasible space, and it's actually slightly easier just to start and end somewhere a little bit outside of that cusp. Now, when we're doing placement planning, we essentially want to verify stability of the object and the placed pose if we do care about that. It also needs to be reachable, so we need to solve for inverse kinematics to guarantee that the robot can actually reach that without colliding with environmental obstacles. And then we'll define the pre-placement pose, oftentimes just by lifting the object slightly, and then we'll plan a transfer path to that configuration. We'll then finally need to ungrasp the object. Now, although this is a pretty serviceable pipeline for basic pick and place, it is a little bit brittle. And so you have to be a bit lucky for this thing to work in the general case. So let's ask what happens in this pipeline if, for example, the first candidate grasp was actually unreachable by inverse kinematics. Well, it seems like we'd have to test that by doing some inverse kinematics, some collision detection, and then ultimately we'd find that it's not reachable. So then we could restart and perhaps try a different grasp candidate. There's other questions like, well, what happens if we picked a grasp and it was something like, I had to reach my arm really way back behind the object, and it's very close to some other obstacles, creating a narrow passage. And then the transit planner ended up having problems trying to reach that target. Well, this would take a long time to plan, and you may not even know that the planning is feasible, even though you may have been spending 10 seconds, 20 seconds, a minute planning. Another possibility is like, let's say, what happens if we grasp the object, but as we're trying to place the object somewhere, the gripper that we chose when we did the whole picking part gets in the way of placing the object where it's supposed to be. Then we've done all this work, and then we finally figured out that this is not a valid grasp, and we'll have to go all the way back to the start. So a general issue is that there's a lot of sequential actions that need to be performed to produce a pick and place plan. And a choice that we make early on that could be chosen incorrectly may prevent a subsequent step from completing, but we don't have information yet about whether or not that choice was valid or not, right? So it's collision-free, it's a stable grasp, but somewhere down the road, it's going to cause a problem. So how do we figure this out? One way that we can think about this is that there's a sort of dependency graph of different items that we need to choose as a planner before we can solve the entire problem. So all of these items here need to be solved for us to be able to produce a pick and place action. We have the grasping pose and placement pose, which require that we reason about the contact mechanics of the situation. We have these pre-grasp poses, post-grasp poses, etc., that are just being determined by these kind of heuristic last inch kind of movements. We then have reachable configurations that we need to solve using inverse kinematics and collision detection. And then we have various motion tasks at the bottom here where we do actual motion planning. So if we just do this in a kind of naive, let's say, depth-first search style approach, where we first find a grasp pose, then we can continue on to produce more components of this sort of dependency graph just by going down here, and then we end up getting a, let's say, transit path. Now we then fill in some of the blanks of the approach path, the lifting path, etc., and everything seems to be fine. We're figuring out that we can go grasp this object, and then everything seems like it's working fine. We'll then find a placement pose for where this might need to go, and then maybe at this point where we try to determine the reachable configuration for the pre-placement pose, we'll do collision detection, and we'll find out that, well, let's say we're trying to load this object into a dishwasher, and we've grabbed this mug from the top, and now we need to load it in the opposite way. Well, we can't do that without our gripper running into the dishwasher itself. So we've done all this work to then finally figure out that there's a collision, and this was an invalid grasp to begin with. So one thing that we can do is a lazy planning strategy, and this is basically a way that lets you prioritize items that are cheap and also that are determinant of the ultimate feasibility of a partial plan. So the idea is that we're going to try to solve items first that are cheap, difficult, and also preconditions for other items to be solved. The reason for this is that we want to actually fail quickly. If we fail quickly, we can throw away our partial work and then move on to the next grasp candidate or move on to the next pre-placement pose, etc. And then we can hopefully then get lucky and find a complete solution after we've failed. A bit of theory about how to deal with lazy planning in a more formal way is a bit of theory about Boolean testing, where each of these tests requires some sort of costly action that needs to be performed. So let's suppose that we need to solve problems A and B, or show that this whole thing is false. This whole equation A and B is false. Now, the fastest thing to do is actually to show that this equation is false, because if this equation is true, then this means that we need to show that both A and B are true. So the fastest way to do this is actually to choose the clause that is most likely to disprove this equation, show that it's false, the fastest. And the way that we can do that is by minimizing this scoring term, c of x over 1 minus p of x, where x is either a or b. Now, if you want to solve an equation that has the form a or b, we have the opposite problem. We want to actually prove the equation is true the fastest, because we don't need to show both of these are true, just one of them needs to be true. And so the optimal strategy here is to minimize the cost of the test divided by the probability that that test is true. Now, if we have an equation that has a conjunction of many terms, we can define an optimal testing order according to the above formulas, and we can also define an expected cost of testing this whole formula as the cost of testing the optimal action if it fails. For an equation that is a conjunction of multiple terms, we can define the expected cost of testing that term as the cost of testing the first term, plus if it succeeds, the cost of testing the next term, etc. This assumes that there's optimal testing order, so that we've sorted A1 through AM in terms of their increasing term C of x over 1 minus P of x. The probability that the overall clause is true is just the product of all the probabilities that the individual clauses are true. We have a similar formula for disjunction that can define the expected cost and the overall probability that the clause is true. Now, if we just take this definition of C of A and P of A, then if we have something, an expression that's in conjunctive normal form, that is a and of several ors, then we can use this equation to determine the truly optimal strategy for testing whether the conjunctive normal form formula is true. Similarly, we can do this for disjunctive normal form. Now, conjunctive normal form, though, is important for sequential plans, because what we're trying to do is find a grasp that works, plus a pose that it reaches it, plus a plan that reaches it from the start. And it doesn't matter which grasp we have. You can use grasp 1, grasp 2, grasp 3, or grasp M, or pose 1 through pose M. And these individual choices are essentially the ors in these ultimate terms, where the terms themselves are, the grasp component, the reaching component, and the transit component. So using this sort of theory, if you took this dependency graph again, the optimal testing order would be to first start with the grasp pose and then move to the placement pose, because these are cheap and they are also likely to determine whether or not we will succeed or fail. So if we do the grasp pose first, we can also do various types of quick rejection tests, such as checking whether the gripper collides. This will, for example, short circuit the transit planning component and the reachable configuration planning component by doing collision checking on things that we know early on in this process. Next, we should then do the placement planning. We can then reject if the gripper collides. And in the case where we were trying to pick up that mug from the top but load it in upside down, this would have already determined that this is infeasible within just 2 steps. Now, if this continues to go on, we can then plan these pre-grasp, post-grasp poses, etc., determine reachability, and then do the planning. And this is a more efficient order than going in-depth first search order. Now this approach will work pretty well, but a really sharp-eyed viewer will have maybe noticed something a little bit weird. So although we've sorted these things in terms of their efficiency to test early on, what happens near the end of planning if we were to, for example, try doing transfer planning and find that we're not able to reach one of these, let's say the pre-placement configuration? Then by just throwing away all of our work, we may have been throwing away work that actually could have been salvaged just by, perhaps choosing a different pre-placement configuration. One general approach to dealing with these sequential decision problems is a technique known as least commitment planning. The idea is that we're not going to actually ever throw away any partial plans that we've explored in the past. Instead, we're going to keep some sort of working set around of all these partial plans, and only if we've determined that there is no solution for one of these partial plans, then we'll always keep these plans available for perhaps future work. So the idea is this: we'll start with an empty plan, and then while we're not done, we're going to pick a plan out from this list of this working set. We're going to try to solve some unfinished item of this plan, and if we found that this is not solvable, then P and all of the other plans that are partially the same plan as P will all be infeasible, and so we'll end up just throwing all of those out. Now, if we do solve the unfinished item, then we can create a new partial plan that adds that new item, the solution, into its item. Note here that we're copying the planning here so that we don't throw away P, but we could return to P if we find that, for example, there's this choice S here may have been infeasible for some future step, so we can return back to P. This allows sort of a very flexible type of backtracking, if you will. Now, if the new plan is complete, then we return it and we're done. Otherwise, we keep going. So there are several different choices here. This is why I call it a meta-algorithm. It's not a true algorithm. But basically, we have the choice of which plan we want to choose to work on next. So we may, for example, prefer that a plan is more complete because we're closer to solving the whole problem. We also want to make sure that the plan has not been worked on too much. So it's oftentimes useful to keep around some track of how much work you've tried on this particular plan. This means that if you've tried really hard trying to solve some plan, it's probably not very fruitful, and you should try to choose a different plan. Another choice that needs to be made is which unfinished items to work on. We've described these Boolean testing-based ordering heuristics, these lazy ordering heuristics, which try to disprove the solution the fastest. And this tends to be a very good heuristic. Finally, we may want to also order by some sort of difference between solutions that have been seen in the past. So if I've tried to solve item I with solution S, and this is very similar to previous solutions in which I've solved I in a similar way, I may want to discount this so that it's not as frequently pulled out from the working set. It's more useful to try a diversity of different partial solutions than it is to try to use very small variations of the same solution. So in any case, this kind of abstract formulation is the basis of the most robust ways of doing pick and place planning, and it will also form the basis of more advanced manipulation planning techniques that we'll look at later on in this course. So as a recap, we talked about simple pick and place planning. This involves the transit, grasp, transfer, and ungrasp phases. We also talked about this usage of the approach, lifting, and lowering and retracting segments of the pick and place planning process, and the C-space justification where these are getting you outside of very deep, narrow passages. We also talked about the benefits of using lazy and least commitment planning, and hopefully these will set the stage when we talk about more advanced manipulation planning later on in this course. Thanks for watching. See you next time.